All right, I am recording my final for stats, intro to stats, and here is my Bearcat card. My M number is M04297649, and I've actually changed my name since I've gotten married. It's actually Kelsey Justice now, so I'm not sure if you need to see my face for the video, but there's that. So I'm gonna go ahead and jump into it. Sorry, my work's a little messy, but I don't have a printer, so I'll have to go to the library and all that good stuff, and you need this video soon, so I'm just gonna go ahead and record it. So question number 1, in this study, 2 independent random samples with interval ratio data were collected. In group 1, a random sample of 133 primary hypertension patients were taken, and each person's total cholesterol was recorded. In group 2, a random sample of 41 normotensive was taken, and their total cholesterol was recorded. Data are given in the table below. Use the 5-step hypothesis testing process to check if the PH group's population average total cholesterol level is significantly higher than 210. And our alpha is 5%. So, given that, we are given our sample mean, which is 214.71, which we can, given there in our table. Our sample size is going to be our 133, and then our population variance is the 879.47. So that's all given to us in this table. So what we're going to do first is we're going to test the hypothesis. So the null hypothesis, we're just seeing if it's equal to 210, and the alternative hypothesis if it's greater than 210. So we need to test these. So basically, we are just checking to see if it's higher than 210, and based on step 1, we can determine that this is a right-tailed test. That'll be a 1 right-tailed test, and let's see, so what else did I write here? For which a z-test for 1 mean population standard deviation will be used. Yeah. Based on the info that's given to us, the significance level is 0.05, and the critical value to match with the 0.05 would be 1.64. So the way I figured that out is, you have your 5%, so you need to use your z-table. And so what you want to do is, I would say the middle here, so like right down the middle would be in between 0.4 and 5. And then the middle of the z-table column, because you're looking for dead center, because 0.5 is right in the dead center. So 1.6 corresponds, let's see, so 1.6 responds to 1.45. Let's see up at the top, 1.45, 1.6, which is just dead center of our data. So I'm thinking 1.64 would be the correspondence with the 0.05 significance level. So now we need to test our statistics here. So we need to figure out if our sample mean, so that basically we have to use this formula. And sample mean, you punch in the sample mean minus the population mean over the standard deviation divided by the total number. So that's when we punch in here. We get our 214.71 from up here from our chart. We're going to minus our 210, which is the cholesterol, the level. We want to we're seeing if it's significantly higher. So that's where we get the 210. And then our standard deviation of 29.66, and we put that over our total population, our total number, of 133. And that gives us our 1.83. So we can finally test, we can observe that the 1.83.1 is significantly larger than our critical value of 1.64. So it is concluded that the null hypothesis is rejected because it's larger. So we can also use a p-value approach. I'm not going to go too deep into that because we use the test statistic, but basically our p-value is 0.0335 and 0.335 is smaller. 0.05 is significantly larger. We can also conclude that the null hypothesis is rejected because we said it was equal to. So basically, to conclude up question number 1, to sum up, I should say, conclude, it's concluded that the null hypothesis is rejected. Therefore, there is enough evidence to claim the population mean is greater than 210 at the 0.05 significance level. So hopefully you're able to understand that, and we're on to the next question. All right, so for question number 2, we're using the same data as question number 1. They're just asking for the point of estimate. So let's see, since it's the same data, I don't have to worry about that. So the point of estimate, we just have to punch into the formula. So we're basically using the first sample mean minus, in column number 1, minus the second sample mean, which would be column number 2. And we just punch in those numbers, so we get the sample mean of 214.71 from column 1, from the pH column, minus 193.20, which we find in the second column. That leaves us with 21.54. And now we just have to use the standard of error formula, and that would be our standard deviation squared over our total number, like this total sample size, which we can find here, which is the 133, over the standard deviation squared, like 2 squared. So that's where we get our 33.04 because it's in column 2, and then we get the 29.66 because that's in column 1. But we're going to square that, and we're going to square this guy, and we're going to put those over our total numbers in the column. So 29 corresponds with the same column, 133. So I put that over that, and then we are going to put it over the 41 from that same column from 33.04. And it roughly comes out to about 5.765. So, let's see, the next part of the question is, can you apply the central limit theorem to estimate the population mean in the primary hypertension patients to low cholesterol? Okay, so yes, you can. And the way that I figured that out is that basically the central limit theorem is used for significantly large samples. So we do know that if it's larger than 30, we can use the central limit theorem. So if it's larger than 30, you're using your sample size here. So we can determine that 41 is larger than 30 and 133 is larger than 30. So we definitely can use the central limit theorem. Now, so here comes some math involved. So we got to use the confidence level. Let's see. So find a 90% confidence interval of the population mean the primary hypertension patient's total cholesterol, and also interpret the meaning. So we here are just going to plug in our sample mean. So we're basically just going to use this formula here, which is our sample mean 1, our sample mean 2, plus or minus our test statistic times the standard of error. So here, I basically punched in, we do know from the previous that our critical value is 1.645, and we're basically we're going to punch that into our formula here. And basically, we determine that 21.51 plus or minus 9.483. So when we do add we do add these together, we get our 30.993. And then when we subtract 21.54 from the 9.483, we get 12.027. So with that, we can determine that we are 90% confident that the difference in the population means lies within this interval. So that's question number 2. Question number 3. Let's apply the chi-square test of independence to our example where we have as a random sample of 500 U.S. adults who are questioned regarding their political affiliation and opinion on tax reform bill. We will test the political affiliation and their opinions on a tax reform bill are dependent at a 5% level of significance. The observed contingency table is given below. Also, we often want to include each cell's expected count and contribution to the chi-square test statistics, which can be done by the software. So, describe the type of relationship between political affiliation and opinion on tax return. So, we basically, we have to check dependent or independent of the two variables, political affiliation and opinion on tax reform. So basically we just have to check the null and alternative hypothesis. Basically I came up with there's independence between political affiliation and opinion on tax reform, which is, like no difference. And then the alternative is there's dependency between political affiliation and opinion on tax return. So basically we need to use our test statistic, calculate the chi-squared statistic, and check the independency of two variables, political affiliation and tax return, use alpha equals 1%. So basically we need to use this formula here, which is our test statistic. So our chi-square equals our sum, that's what that symbol is here, which is observed frequency minus expected frequency squared over which is E, which is our total times column total, row total times column total divided by grand total. So we need to use this formula to find our chi-square table, which is going to help us find our chi-square here. So our sum basically. So O is given to us right here in our chart. So we get the 1. All right, so we're going to our observed frequency column here. So like I was saying, you get it right here from our chart, the 138, 64, all the way down, 64, 67, so forth. And then you have your expected column, then you have your observed minus expected, you have your observed minus expected squared. So all you're doing is punching these numbers into this formula here at the top of each column. And then you have your expected observed minus expected squared over the E. So basically when you punch in all of, you get your total sum here, your sum, which I got 22.15. So that would be our chi-square sum. And then we need to figure out the degrees of freedom. That's our number of rows minus 1 times our number of columns minus 1. That's given to us here. We have 2 rows and then 3 columns. So 1, 2, 3, and then 2 rows. So we get 2. And then the level of significance is 0.01, which was given to us. I know that was given to us. Yeah, alpha 0.1 or 1%, which would be 0.01. And then we find our critical value by using the chi-square table would be 9.210. So our test statistic is greater than our critical value. So because our test statistic is greater than our critical value, so we can reject the null hypothesis. So because we said an independence between opinion, political affiliation and opinion on tax return. So we can reject that, and my conclusion is there is dependency between political affiliation and opinion on tax reform. All right, so for question number 4, this is a long one. A sample size study is conducted involving 15 infants to investigate the association between gestational ages at birth, which is our X, measured in the weeks, and birth weight, which is our Y, measured in grams. So we were provided this chart here, which provides, the weeks and the birth weight in grams. And basically the first question is calculate the Pearson sample correlation coefficient R and interpret its meaning. So we're gonna do this tedious chart here. We have X is our gestational age, which is our weeks, which is our independent variable, and we have our birth weight in grams, which depends on the age, etc. So we have our X column, which is given to us, which is our gestational age in weeks, and then we have our Y, which is our birth weight, and then we are going to X square it, Y square, and then the sum. So like X times Y. And then down here I have the totals, which we'll get to that in a minute. So we are basically going to punch all of this in to a lovely equation here. I'm sorry, it's kind of messy, but basically our correlation would be the sample size times the sum of xy minus the sum of x times the sum of y over the square root of n times the sum of x squared minus x squared. Times the sum of x squared minus x squared times n times the sum of y squared minus y squared. So you plug all that in into the equation here, and we get 0.8793, and that is our R value. So I just wanted to put that out there. But there's an easy way if you didn't want to do a total, like put it all into one equation, is you can also do the sum of x over n, which would be 38.36. And the way I found that is because the sum of x, our total is 575.4, and then our 15, we get that because we're involving 15 infants. So you know that way, and you get your 38.36. Same thing with the sum of y over n, you get, your 2976.6. So forth. You keep going all the way down, x squared, y squared, and then you multiply them. And then I have these numbers here. We basically just punch it in like I was just doing. So like I was saying, the correlation coefficient of R is 0.8793. And basically we can interpret, since R is 0.8793, we say that there is a strong positive linear relationship between gestational age and birth weight, because it is greater than. So test the hypothesis for a right-tailed alternative at 5% significant value. So we are going to test the null hypothesis equals 0, and then the alternative is equal to or greater than. So we do know that our R equals 0.8793 from the previous page. And then our sample size is 15, and our degrees of freedom would be 13 because n minus 2, which would be 15. So here it is, 15 minus 2 equals 13. So let's see. We find the critical value using the critical values table at 13 degrees of freedom on a one-tailed and 5% level of significance. So the critical value would be plus or minus 0.441. And since our R is 0.8793, we can conclude that 0.8793 is larger than our critical value of 0.441. So R is significantly larger, and the line may be used for prediction. The alpha line may be used for prediction. The line best fit of y on x, we're going to punch into this equation here, and we're just trying to find the x and y slope. So basically pyx equals our xy times x times y over our observed squared times x. So basically what we get is 1932.897 over our 10.6104, which would give us our 182.17, which is gonna be our slope. And then so basically to test the hypothesis, we have to use this equation here. Y minus y equals, or the sum of the y minus the sum of y equals b times y times x times x minus the sum of x. So we need to test that. We need to find b basically, and how we're going to do that is we're gonna punch in the numbers that we were able to find. So we basically want to use our slope, and basically we just punch it in here. 297.6 equals the 182.17, which we got from here, and we're going to multiply that times our x minus, we know it's 38.36 because we got that from, where did my thing go? Here we go. We got it from here, 38.36, and then, or really essentially from the sum of x over n. That's where we got the 38.36. So, sorry, I'm a little disorganized. I've done this like 4 times. Minus that 38.36. So we take our slope, which is the 182, minus, we punch these in, and we get our y-intercept of negative 4011.4412 plus our slope. And then, and to estimate y, so the last question says, fit the line of best fit y on x. Use this model to estimate y when x equals 18 weeks. So basically all you would do, since we didn't, you just plug in 18 for x. So we're going to use our intercept plus our slope times 18, because we're going to just punch in 18 for x. And then once you punch all that into the calculator, you get negative 732.3812 at 18 weeks. So